Greetings to all and welcome to this lecture. We are in module 3, which is 2-terminal MOS structure, lecture number 2, reason of operation. As we have seen few reason of operation earlier, that is depletion and accumulation, in this lecture we will discuss the inversion. So let's get some insight into the inversion reason, which is obviously an important reason of operation for MOS cap structure. In this lecture we will see what is inversion reason and a few of the approximation which will make our model framework or a mathematical framework easy. These are the learning outcomes of this lecture, which will help us to understand the principle of depletion approximation and the charge sheet approximation. Let's do a quick recap. In the previous lecture, we have discussed that when you applied a gate to body voltage in a 2-terminal MOS structure, so you have metal, oxide and semiconductor. When you apply a gate to body voltage, based on the gate to body voltage values, the surface potential varies, and if the gate to body voltage is negative, then surface potential will be negative, which causes a positive charge in the surface. That positive charge is dominated by the holes. When you apply a gate body voltage positive, then surface potential becomes positive, and hence the charge which is coming up the surface is given by immobile ions. When you further increase the gate to body voltage, the surface potential here at the surface will increase, and near around 2 phi f value the inversion comes into picture. So we have already seen the relation between the gate to body voltage with surface potential. We saw that surface potential is negative in the accumulation region, then when you are increasing the surface potential towards positive, so until phi f this is approximately linear, or after phi f also this trends go on, because the majority of the channel charge is governed or dominated by the immobile ions. So this value is 2 phi f. We also derived one equation for a surface potential in this region, and we termed it as psi SA, where psi SA was given by minus gamma by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage whole square. Here gamma is a body effect coefficient. Now let's see. So we have already seen what will be the channel charge in accumulation and what will be the channel charge in depletion. We have considered two extreme cases, deep in accumulation and deep in depletion, to extract or to simplify our model framework. We found that QC dash exponential dependence with psi s, so minus psi s divided by 2 phi t, and that's what the reason we are getting exponential rise when we are plotting the QC dash with respect to psi s. We have seen that in depletion region the QC dash is governed by immobile acceptor ions, and hence there is not a significant change into the channel charge by a significant change in the surface potential. So these are the equations we extracted with using some good amount of approximation that the channel charge and surface potentials are related in such a way in given accumulation and depletion condition. By solving this equation, we extracted psi SA. Now let's see what will happen if you increase the gate to body voltage in such a way that the surface potential will increase beyond 2 phi f. If that is the case, then the increase in gate to body voltage will causes more positive charge into the gate, and hence your QG dash becomes more positive. As we have seen that by using charge balance equation, the QG dash can be given as, or the change in QG dash can be given as the change in QC dash in a negative direction, or in principle when you are applying a more positive voltage, the depletion region extend, and after a particular depth the expansion of the depletion region will stop, and hence the inversion occurs, meaning the electrons from the p-type body will come near to the surface. So this is electrons. it means the total channel charge now can be captured or governed by two types of charges. One is Qi dash. So we are defining few new parameters. One is Qi dash. Qi dash stands for inversion charge, and Qb dash, this stands for depletion charge or body charge. So B stands for body here. Again, if I am using dash, meaning the charge per unit area. So when we are in inversion, so you have applied VGB in such a way that when we are in inversion, then the charge is predominantly governed by immobile ions and the electrons. So by using the approximation, we can simply ignore the whole contribution. If we ignore the whole contribution in our complex formula what derived in previous lectures, QC dash, we can simply ignore the term of whole contribution. So let me rewrite. QC dash was given by minus of signum psi s square root of 2 into Q into Na into epsilon s square root of phi t plus psi s minus phi t plus exponential of minus 2 phi f over phi t e to the power of psi s by phi t into phi t minus psi s minus phi t. We have seen that this term contributes the whole, this term contributes the immobile ion, and this term contributes the electron concentration. We can simply use our common understanding that we are talking about psi s is positive. If psi s is positive, this term is decaying exponential, and you can simply ignore that part. So whole contribution can be ignored when we are talking about inversion. Psi s is positive, so you cannot ignore this term. Again, psi s is positive and this is a positive exponent. So positive exponent is give you the larger value, and hence ultimately you will get this expression. Point to be noted here that this QC dash is a total charge when the surface potential is increases beyond phi f. This total charge can be given by inversion charge plus the bulk charge or the depletion charge. Now, by using some different understanding, we can simply extract Qi dash and Qb dash such that we can get the total charge. Or if you have an equation for total charge here, which is QC dash, can I get an equation for Qi dash or Qb dash? So let us do a first approach to try to calculate Qi dash. What we will do is, we are considering that this is a two terminal MOS structure. You are applying VGB in such a way that positive gate charge will come up here. This positive gate charge causes a negative charge, and hence the immobile ions will come into picture. After this immobile ions, the electrons will come near the surface. Correct? Now, one can see this is the potential, what we called it as surface potential. If we are considering in term as a function of y, so this is y and this is x, correct? So again, if we do general analysis, this can be considered as psi y. Now when you move from the surface toward the body, what will happen? This psi y will be decreasing. If psi y will be decreasing, it means some point will come up when the inversion charge is also decreasing, and hence you can fix a point as yc, and we can assume that there is a sheet of carriers or sheet of inversion charge like that, which is present near the surface. This point is y surface and this point is yc. Now if I am interested in to calculate what is the total inversion charge, now what I can do, I can consider a small strip of delta y. So this is a delta y, right? And the total charge, if I will integrate, I will get what? The inversion charge. So if I am interested in to calculate inversion charge, what I will do, the total charge present into small incremental height of delta y can be given by ny into delta y into q with a negative sign, right, and this is a 3D structure. It means you need to multiply with area, so this will become the total charge. You need to integrate this charge from y surface to yc. But in our course, as we are only dealing about the charge per unit area, you can simply divide by this area and you will get the total inversion charge, which is qi dash, was given by y surface to yc minus q times of ny dy. Here the ny is actually related with the psi y, because we have already derived the general equation for ny, which is the electron concentration near the surface can be given by n naught e to the power of psi y by phi t by using junction law. Here n naught is the minority carrier concentration in the body. This is the one approach which helps us to calculate the value of qi dash in the two terminal MOS structure. But this is a tedious job, because we do not know much about what is the depth or what is this limit yc. This is really not very easy to find a sharp boundary when the inversion layer charge exists. Instead of using this approach, can we use some alternative approach to get the inversion charge? If you see that the total charge is given by inversion charge plus the bulk charge. By using approximation, I have the closed form equation for the total charge. If by some sense I will calculate the bulk charge, then from here I can calculate the inversion charge, which is nothing but the total charge minus the bulk charge. So instead of following this approach to calculate the inversion charge, let us do some other approximation and find out qb dash. If we will get the expression for qb dash, we will go and calculate qi dash by simply qc dash minus qb dash. To get a good amount of approximation to calculate qb dash, we will consider two approximations here. One is called depletion approximation. This is the same approximation we generally use when we are deriving the diode current equation in p-n junction diode. If you remember, in p-n junction diode we have p type and n type semiconductor, and there will be a built-in potential coming into picture because of this depletion reason. What we say there is, depletion approximation means in the depletion region there is no mobile charge carrier present, and hence the depletion region is completely made up of immobile ions. That is what we are going to consider here. What we are saying, when you are applying a gate to body voltage across these two terminal structure, then based on this voltage, the positive charge requires a negative charge at that another plate or in the semiconductor surface, then the uncovered immobile ions will come into picture. Correspondingly, we have electron inversion layer also. But what we considered, that this region is completely depleted and it can be given by a sharp boundary of height dB, where this dB is nothing but the height of or the depth of depletion region. If we are interested to calculate the total charge present into it, we can simply use this condition where we plot the charge density, and hence what we will do, we will divide the per unit area, because we are interested in or we are dealing with the quantity charge per unit area. So qb dash was given or is given by qb per unit area, right. The another approximation what we are considering here is charge sheet approximation, which says that the depth or the thickness of this inversion region is very, very small. It is like you are applying a positive voltage, there will be a depletion charge and then there will be an inversion charge. What we are considering, the thickness of the inversion layer is very, very small, and hence if this thickness approaches to be 0, so delta y approaches to 0, the potential drop across that zero thickness of inversion charge is almost 0. So you can consider that the potential drop across the inversion region, inversion layer, is almost 0. Then the total surface potential will drop across the depletion region only. This is a good amount of approximation what we are using to simplify our analysis. Let's see how these approximation will help us to simplifying the analysis. What we are doing here, we are plotting or we are analyzing the charge density, electric field and the potential graph of our two terminal MOS structure. This is same as what we saw in PN junction. So this is gate terminal, this is body terminal. If we see what kind of possible charge are present, then you see this is a gate charge which is positive because you are connecting a positive voltage out of it. So the gate charge is almost near to the surface because the gate is made up of metal and having equipotential. So the charge will exactly appear across metal and silicon dioxide interface. So this positive charge is very, very high, and hence we can show by some discontinuities. There is also positive charge present at the oxide, which we termed it as Q naught dash. This positive charge is fixed and depends on particular fabrication process. Because of these two positive charge, there is negative charge coming in the surface in depletion and inversion condition. So what it can be? It can be given by immobile ions, and this extension is dB, the extension of depletion width. There is a small thickness of inversion layer which is also very, very high, and hence we need to show by discontinuity. If you see this charge density curve along the device dimension, will get this figure, and it says that all the possible charge is actually in balance. Considering the depletion approximation and charge sheet approximation, we can simply say that this thickness can be ignored with respect to this dB. Now the total charge, the total body charge is now can be given as, or per unit area is can now be given as minus of Q into Na into dB. It's nothing but thus the area of this region. The area of this region will give me the total charge. So the total charge per unit area is can be given by minus of Q into Na, which is this value, into this height. Correct? Now by using basic electrostatics, we can find the electric field. So the electric field is nothing but 1 over epsilon integration of, which means I need to simply integrate this curve, which will give me the electric field curve. Integrate means you need to calculate the area. So let's start calculating the area. This charge, which is a gate charge, is nothing but it's simple as an impulse function. The integration of the impulse function will give you a step rise here. Now here the electric field will be constant in the oxide region. However, you will get a sudden fall in the electric field here. This electric field is the electric field value at the semiconductor surface. We called it as E body. So this electric field value and this electric field value have a sudden drop. Why it is so? Because the electric field or the electric flux should be continuous, because you are changing two different materials. There is a boundary where the two different permittivities are coming into picture. One is silicon dioxide and one is silicon. So you need to use a boundary condition which says that dOx should be equals to d of Si. This can be written as epsilon Ox into Eox is equals to epsilon of Si. Instead of Si we can use body. So this body into epsilon of or E of B. I am interested in what is the value of EB. It can be given as Eox or epsilon Ox divided by epsilon of B into Eox. This value is approximately 3.9. This value is approximately 11.7 Eox. meaning if you see 1 over 3. So, whatever be the field you will get at the semiconductor surface is approximately 1 over 3 times to the electric field which is appearing at silicon dioxide. Now, how can I calculate this electric field? Again, we can simply calculate the area of this square or rectangle. The area of the rectangle can be calculated as Q into Na into dB divided by epsilon s. So, by using this electrostatic, we can calculate EB, which is the electric field at the semiconductor. Now, further, how can I calculate the potential drop across this depletion region? The potential drop from this electric field graph is again can be calculated by using integration or by using calculation by calculating the effective area. So, the effective area of this triangle can be given by half of, so this is nothing but psi s surface potential, half of EB into dB, where dB is this height. This expression will give you the effective surface potential which will drop across the depletion region. Let us use dB from here and put into this surface potential equation. So, psi s is equals to Q times Na dB square divided by 2 into epsilon s, or the height of the depletion thickness, or the depletion thickness can be written as dB is equals to square root of 2 into epsilon s into psi s divided by Q into Na. So, by using this, we can simply calculate what is the total bulk charge or body charge. So, QB dash was given by minus Q into Na into dB. So, if you put dB, you will get minus Q into Na into dB value is 2 into epsilon s into psi s divided by Q into Na, or this can be given as minus 2 Q Na into epsilon s into square root of psi s. So, this is a simple form of equation which relates the bulk charge with the surface potential. Now, I am interested in to calculate what is the inversion charge. So, we have already discussed the inversion charge can be given by the total charge minus the bulk charge, and hence you go back and put this bulk charge equation into that equation, you will get Qi dash can be given by minus of square root 2 Q into epsilon Na is common, and this term was available into Qc dash, and this term you have just subtracted. So, out of which you will get what is the total bulk charge and the inversion charge. So, this expression can be plotted here, which shows that what is the total charge here, right, with respect to surface potential. Now, it is the time to bifurcate the inversion region in different region of operation, which can be considered as weak inversion, moderate inversion and strong inversion. What is that? When you increase the VGB voltage, then, so let us consider you have 2 terminal MOS and you are increasing the gate to body voltage. So, when increase in gate to body voltage increases your surface potential. So, the surface potential reaches to value of phi f, which gives you the depletion, but beyond the depletion there are some amount of mobile ions present, though for simplification we considered that the concentration of these charges are negligible, but they will give some amount of conduction when this 2 terminal MOS become a part of MOSFET. So, using the depletion approximation and charge sheet approximation, we found that the psi s is approximately dropped here across the depletion thickness, and hence the total charge, which is related as 2 into square root of 2 Q N A into epsilon s into this. So, if we are going to plot this equation, so this will be minus square root of 2q Na into epsilon s into square root of psi s. When you are going to plot this, it looks like this. You are plotting the total charge with respect to psi s. So, this will give you qb dash, and qb dash is approximately constant even beyond phi f. This is considered as onset of weak inversion, and this is the maximum limit of weak inversion. So, till that point you consider that qb dash is almost constant, which is varying as directly proportional to square root of psi s. Now, the inversion region or inversion charge will exponentially increases beyond 2 phi f. So, this is your inversion charge. Because of exponential dependency, the inversion charge increases beyond 2 phi f, and if you take a sum of this graph will give you the total channel charge, which is nothing but qi dash plus qb dash. So, we will discuss this graph in more detail in next lecture. Let me summarize this lecture. Here we have discussed the importance of inversion region in two terminal MOS structure. In two terminal MOS structure, when the surface potential is increases beyond phi f and it become less than 2 phi f, then this is called weak inversion, meaning you have some immobile charge carriers present into the surface which is predominantly governed by depletion region, but there are some amount of charges which are present, but we consider the overall charge is captured by the immobile ions. We have also seen some approximation like charge sheet approximation and depletion approximation makes the model framework easy, and hence we derived the closed form equation for inversion, which is 2q Na into epsilon s square root of psi s plus phi t e to the power of minus psi s minus 2 phi f by phi t. This become plus, right? And we derived the inversion charge can be calculated by qc dash minus qb dash. So, we will stop here for today. Until then, take care.